Today we are going to talk about a limit of a function in two variables. Let me start with the definition of a limit existing in R2 if we have a function of two variables. So let's start with a function f, which maps R cross R into R, defined as follows. F of AB is equal to C, where A, B, and C are real numbers. We say that in two variables a limit exists. A limit in two variables is written this way. So we say this limit exists means that as the variables x, y, which are sets of ordered pairs in R2, get closer to a fixed point of interest, namely AB, that the function and the limiting value get arbitrarily close to each other. So that can be stated using the traditional delta epsilon definition of limits in two variables, which is an extension of the definition of limit in one variables. So the definition is as follows. For every epsilon greater than 0, there exists a delta of epsilon greater than 0 such that the absolute value of the distance between these points, remember we're in R2, so we have to define a metric that makes sense. A and B is my point of interest, where I'm interested in calculating the limit, and x and y are the locus of all points that are equidistant by some fixed distance d between the fixed point AB and my variable points. So consequently they tend to form a neighborhood, or circle, around the point AB. So we can define our Euclidean metric to define distance. So we can talk about, say this is point A and this is point B. We can talk about the absolute value of A minus B. Or we can define that using the traditional distance metric, which is how to calculate the distance. Well, it's this formula, x minus A quantity squared plus y minus B quantity squared. The sum, that entire sum, gets square rooted. So we can say for every epsilon greater than 0, there exists a delta such that this, the square root of x minus A quantity squared plus y minus B quantity squared less than delta, implies that my functional value and L are within epsilon distance of each other. So let's do an example in two variables. Let's say we have a function f of xy defined as follows. It's x squared y over x squared plus y squared when x and y are not equal to 0, 0, the origin, and it's defined to be 0 at the origin. So one might be interested in saying whether this limit exists. So we have x comma y approach 0 comma 0 of f of xy. Is that in fact equals 0? And it might be reasonable to think that this limit equals 0 because at the origin the function is defined to be 0. So if we use the delta epsilon definition of limits, which I'll denote as star from now on, and of course we're cognizant of the fact that A comma B correspond to the origin, we have the following proof that has to be done. We have to show that the square root of x squared plus y squared less than delta implies that the absolute value of x squared y over x squared plus y squared minus 0, which is the limiting value that we believe this function converges on, is less than epsilon. As usual with delta epsilon proofs, we have to begin with the end in mind. So we have to show that this results in this as a consequence. So if we start with the absolute value of x squared y over x squared plus y squared, we know that that's equal to the absolute value of x squared over x squared plus y squared multiplied by the absolute value of y. And we know that that is less than the absolute value of y, because this quotient is less than 1. The numerator and the denominator are related insofar as the denominator exceeds the numerator. So we know this will always be a fraction less than 1. Now we know the absolute value of y is less than, certainly, the square root of y squared plus x squared, because the square root of y squared is defined to be the absolute value of y, so if we add a little bit more, we know that that exceeds, is an upper bound on the absolute value of y. And we're starting with this as a premise that this is less than delta. So my proof can be done if I choose delta equal to epsilon. Therefore, I'll start with this. So here's my proof. I'll begin with this. And then I can say that this is equivalent to the following statement. That's greater than y, absolute value of y, and that exceeds, certainly, the absolute value of x squared over x squared plus y squared times the absolute value of y, and of course that's equal to the absolute value of x squared y over x squared plus y squared. And what do we have? We have that the absolute value of f of xy minus L is in fact less than epsilon, and our proof is complete. When a proof is complete, we can write QED.